Okay, hi everyone, and welcome to the, last March webinar. I was thinking it might be the first April webinar, but no, it's the last March webinar from the MAPP program. And the topic of today's webinar is Model Infrastructure for Improved Model Performance and Interoperability. And we have three speakers today. We're going to hear first from Balaji from Princeton University and GFDL. Balaji is going to talk about common model infrastructures and how they're used in the construction of Earth system models, as well as multi-model ensembles. And then we're going to hear from Cecilia DeLuca, who's out at NOAA Center, and she's going to discuss the Earth system modeling framework, ESMF, which is an infrastructure and software package used by modelers at multiple agencies and modeling centers, including NASA, NOAA, NCAR, Navy, and other centers. And then finally, we'll hear from Mark Iredell, who's at the NOAA NCEP Environmental Modeling Center, and he's going to discuss the NOAA Environmental Modeling System, otherwise known as NEMS, which is used as a software structure for operational models at NCEP. So, Balaji, are you there?
Yeah, I'm here.
Okay, great. I'm going to swing control over to your computer now.
I hope you can see my screen.
No, not yet. You make sure you hit the Share My Desktop button. You might have to flip back. Yeah, there you go. All right.
All right. Is that good?
Yeah, it looks good. So whenever you're ready, go ahead.
Okay, thanks everybody who made it to the call. So my talk is going to be on common modeling infrastructure, and it's used in a number of different senses. So I'd like to talk about what are the scientific roots of going towards common infrastructure and what purpose it serves, and how we use it today and how we should be using it in the future. So let's start by looking at a famous figure, which is from the Summary for Policymakers of the IPCC AR4 report. So this is a kind of picture that's produced from multi-model ensembles which are used for climate projection and are widely used in this sense. So what this picture is showing is both for the historical period an ensemble of 42 models. That's what that number 42 means. And the black line is the mean of all those models. And then a set of models which are used for two different sets of projections into the future, the RCP 8.5, which is the warming scenario, and the RCP 2.6, which is the less warming, the more controlled emission scenario. And there's 39 models and 32 models. So you can see that you can see both the spreads. So the gray bar on the left shows the 90% spread across the models, and the black line is the average. So you can see one thing that's kind of visible here is that over the historical period, there's a somewhat narrow spread compared to the spread over the future. And that raises an interesting question. So to what extent are results reproducible across models? Is it possible, for example, to take a result from one model and reproduce it in another? And it turns out that that's actually not very easy to do at all. It's pretty hard. So there are examples. There was an NRC report a few years ago which picked on some examples where there are two models. If you compare the historical record, you would say that they are of equivalent skill. And then you take some phenomenon and project it out into the future from these two models, and you will find that for the same forcing scenario, they make opposite predictions. The example that they used in that report was one of Sahel drought. So they did talk about what this means, implies for multi-model ensembles and so on. So this is the NRC report. The URL is long and complicated, so I'll just let you Google it if you want to find it. And they made several recommendations about how common modeling infrastructure is used and how it can advance the science. So the first point to keep in mind is that there's a thing that we call structural uncertainty, which is different models developed by different modeling groups. They may represent a certain process in the climate system differently. So there are different representations of the same thing. So that is called structural uncertainty, and common modeling experiments, what they do is they help you run the same experiment using two different representations and then look at the differences. And that will teach you something about both the phenomenon and about the models. So they did recommend that you can maintain modeling diversity, but there are some parts of the climate system where there is perhaps less structural uncertainty, and then there's more consensus, and there maybe you can use common infrastructure to narrow the points of difference. Additionally, the report also recommended that the global data infrastructure is very critical. So that is something where we make, if two models are running the same experiment, we need to be able to share our data. And there are some requirements arising out of that. And they also recognize that this infrastructure is very critical to us, yet it is not funded as though it is critical infrastructure. So they made some recommendations. They also talk about nurturing a unified weather climate effort. And what that means is that you can use methods that are used in NWP to address biases in climate models. It's found, for example, that certain biases in climate models show up very quickly. So there are long-term biases in the model, but even with a very short run, you can, the patterns, you can get them from a very short run. So they said you can use NWP methods to try and understand the biases in short runs. Similarly, if you take weather models and run them for a long time, you'll find problems of climate drift and non-conservation which you can address. And they finally recommended that there should be a forum to promote this kind of sharing. So you identify key scientific challenges, you design common experiments, and you set the standards for data interoperability and shared software. When you do that, you get interesting results of this kind. So this is the result from the CMIP 3 era, Reichler and Kim paper, which compared models' abilities to simulate the 20th century climate. So it's some metric where to be on the left is a good thing. That means you have a better model. And it's compared against the 20th century simulations against some reanalysis. So the reanalysis would appear on the left edge of this plot over here if it were plotted, right where my cursor is. These are 3 generations of models. So CMIP 1 was from a few years ago, from 15 years ago. CMIP 2, this is the 2004 report. This is the 1999 or 2000 report, and that's the 1995 report. And you can see that the models have a certain spread. The gray is the median model, and the black dot is the average of all the models. That means you sum up all the models and you take the average. And you see that the average is actually better. The models are getting better over time. Everything is moving to the left. The average model is generally better than any individual model. Doesn't have to be the case. For example, if you go back to CMIP 1, you find it's in fact not the case. And the models are getting better over time. You can see that, for example, if you look at the median model in CMIP 2, it would be one of the lowest models in CMIP 3. So the models, in fact, are all getting better. And also the clustering is improving, which means that whatever we learn from one model, it goes into other models fairly quickly. An even more interesting analysis, which is more recent, is from a paper by Knutti et al. In 2013, where they looked at what they call the genealogy of climate models. And you can use an analogy if you studied evolutionary biology or paleontology or something. There are diagrams made like this to discuss how closely species are related. So the way this plot is made is you take 2 models, and here the distance is computed just from data. So you know nothing about the model. You just take the temperature and precip data and from 2 models, and then you compare them and see how similar or how different they are. And using this metric, you can sort this so that if the link point on this diagram, which is called the dendrogram, is further to the right, it means the models are less closely related, and if they're closer together, it means they're more closely related. So you can think of this as phenotypic distance. That is, by looking at 2 species, you're deciding how close they are, like a dog and a wolf, for example. And the genetic distance is how closely they're actually related in terms of code. And there you see, for example, you see clusters of the same color. These are models that are actually closely related in terms of sharing components. So there's a red cluster for CESM, there's a green cluster for GFDL, and a purple cluster for UKMEP. So these models are actually closely related. And what this diagram is telling you is that actually, models that are closely related genetically, you can say they're also closely related phenotypically. And this is a nice finding, and why should this be the case? And the paper discusses various reasons why this might be so. So if you look at how these various centers are building Earth system models, you have first what I call the notional architecture, which is an Earth system model is composed of atmosphere, land, ice, and ocean, let's say, and then the atmosphere is composed of a dynamics component, which is called the dicore, and a physics component, which is all the stuff that you don't resolve in the dicore. And the physics can be split into a radiation component, a moist physics component, which are called H2O, and a planetary boundary layer. The land can similarly be split into a biosphere component and a hydrology component, which I'm calling H2O, and so on and so forth. So you can have multiple components. But in fact, in code, you may not be building it with so many components. You can code them up differently. So different models embody this differently in code. And there was a very interesting poster from two Canadians at AGU a couple of years ago. You can go and find this fairly easily. So they compared the software architecture of global climate models. You don't have to look at all the details, but these are various centers. So there's one, Cosmos is the Max Planck model, Model E is the GISS model, GFTL is here, CESM is here. These purplish things mean atmosphere. If it's a kind of orangish thing, that means land, and bluish things are ocean. And just visually, you can look at this diagram and you can tell that the architecture of is not similar at all. So each one actually writes code separately. In fact, there are key differences, such as in some cases the land is inside the atmosphere and in some cases it's outside, and that sort of thing. So it's not that easy actually to do these experiments where we just say we swap components between models. It's a good thing to aim for, but it's actually hard to do in practice. And the physical architecture of a model, what fields they actually exchange, is also fairly model specific. So as an example, I'm showing you what it is in the FMS coupled architecture. And this is the modeling system that's run at GFTL. And without going into details, let's say you wanted to take this diagram. So it shows an atmospheric component, a land, ice, and ocean component. And in between there's a surface, there is a separate component which we call the surface boundary layer, which exchanges fluxes between different components. And without going into too many details, you see that these models are fairly specific about what they expect to receive and send. So for example, the shortwave in our model is split into 4. There's 2 bands for direct and diffuse and 2 for near infrared and visible. So if the model is expecting that, then if you couple in a different model, they have to be able to supply fields like this. And there's a second complication, which is that some of this stuff is using an implicit time step. The vertical diffusion is done implicitly. So some fields are actually, which I'm calling, there's a whole bunch of fields in there which are passed back and forth, which I'm calling R, which go in both directions. But in general, fluxes go down, state variables go up, and excepting for the implicit part. So if you actually were to do this exercise of taking out one ocean model and putting in a different one, you would find that the software part of it, which is like actually having calls in there and all that, is the simple part. And the actual hard part is figuring out what physical fields go back and forth and then coupling it in a way that runs numerically correctly. And it turns out that if you want to do certain things which we do for computational performance, we are now thinking of extending the component parallelism to an order of about 10 things running in parallel. And you see that the coupling time step actually is a very specific technical issue. So it's not easy to change this across models without changing answers in a particular way. So if you take 2 components, which here I'm just calling ocean and atmosphere, and if they're coupled serially, they have a certain kind of time stepping scheme, which is called a forward-backward time step. If you actually made them run concurrently, they would have what's called a forward-only time step. And this system is actually, if you do the numerical analysis, you find that it's actually unstable. It happens to work in practice in many cases when you have a damped system, but I put an asterisk on damped because every system that you study is not damped, so you will occasionally run into problems if you do the system. But we do it, and for the new coupling, for the new systems, we're actually thinking of moving towards much more concurrency at the coupling level. And this means that you're actually writing a fairly different physical system, and it may not be easy to translate different models to run with the same kind of thing. So as an example, here is something we're trying to build at GFTL where the radiation code is running concurrently with the atmosphere, for example, using shared memory, whereas the atmosphere and ocean are running concurrently using MPI, or communications. So these kind of architectures are under development, and each of these will have a different implication for the physics of coupling. So we have to be very careful when we are talking about like building a common infrastructure for different models. So the other question, of course, is that supposing you could, in fact, let's just theoretically as a thought experiment, construct all the models of the world from a single code base. So you would just pick and say, if I pick this, and this component, I get one model. And if I pick another set of components, I get the GFTL model. And if I pick a third set of components, I get the Hadley Center model. Would that be a good or a bad thing? So is there a reason? And of course, returning to the NRC report, it did suggest that there is still a lot of uncertainty in our understanding, so we should maintain diversity. And there are certain things where there may be less controversy, and maybe you would be able to reduce diversity there. So I'd like to kind of stop here with a summary slide. I just want to point out, I don't know if these are actually conclusions, but sharing infrastructure is actually a hard problem, so don't just assume it's a very good idea. And you must do it with a specific purpose in mind. I think the scientific reproducibility of simulations is a good thing. You should be able to understand why two simulations are different from each other. And there are a lot of things that are needed if you want to achieve that. The second thing is that if two people want to, if I want to set up an experiment and then my colleagues Alice and Bob want to join me, we should be able to run the same experiment with our different models and compare the results. That process should become lightweight. It's pretty heavy right now, the process of what I'm calling setting up a MAPP. We should recognize the diversity of models, recognize the diversity of coupling architectures, and that the diversity actually has a scientific purpose and value. And interoperability and shared infrastructure has many, many aspects. So it includes common experimental protocols, analytic methods, documentation standards for data and data provenance. We can share workflow, we can share model components, which we call superstructure, and we can share technical layers, which we call infrastructure. So all of these are important, but I'd like to stop here and take questions. Thank you.
Great, thanks a lot, Balaji. Very interesting. Any questions? Actually, before I go to questions, I want to remind individuals on the line and those who haven't attended before that you should send a question to me using the chat feature, and then I can unmute your line so you can ask it of the speaker. So please utilize the chat feature, send me a question. I don't have any questions from anybody on the line yet, so I'll see if anybody in the room here has a question, or Cecilia and Mark who are on the line. If you have questions, feel free to ask.
Balaji, this is Rick Rosen. Sharing infrastructure is a hard problem, but why is it naive to believe that something like the Earth System Modeling Framework isn't designed to solve that problem?
I think, Rick, in fact is designed to solve the problem, but I think, as I was saying earlier, there are a lot of very nitty-gritty issues that ESMF has nothing to say for or against. It's a standard template for coupling these things, but then you have to do the hard problem. So we are going through the exercise right now, GFTL and NCEP and ESRIL, of coupling GFS with MOM5. And actually getting the mechanics of coupling was the easy part. The hard part is actually deciding what fields go back and forth, how they're coupled, and in fact, a landmark we've achieved today is that the model has crashed. That means we're actually running it, and it's reached the point where we are trying to figure out what's making it go unstable. So that's where I think the real problem begins. Actually, ESMF is where the problem, it's not the end of the problem, it's where the real scientific problems begin. That's how I would say.
Any other questions?
I will just comment that I'm not sure that subtlety is widely appreciated. So your having talked about it today, I think, is very helpful.
Yes, thanks, Rick. I understand that. So I put in a little comment here, which is never say plug and play. I think that was one of the things that people did misunderstand this in the early days of ESMF. They thought that if everybody used ESMF, we'd just be able to move components back and forth very easily. But the scientific problems of coupling are very hard. And I have to say the NRC report did recognize that. It did use the phrase the science of coupling. So there's a lot of numerical and algorithmic issues about coupling. It's not just a software issue.
Very helpful. Thank you.
So Balaji, there is one question here from Chris Bretherton, and I'll ask it, but I'll also will unmute Chris's line so he can ask a follow-up. His question is maintaining diversity desirable?
Is maintaining diversity desirable? I think yes. I think there are many processes for which we do not have an idea, or the right idea of how to represent it. So anything in Chris's line of work, for example, I think there are still many ways of doing things. You know, interactions between clouds, aerosol, and radiation, for example. So yes, I mean, I certainly think so. But I also think, in some senses, I mean, this is science. So if Sarah comes along and she has a new way of running a model, I mean, I don't see, we can't tell her, sorry, the quota of models is up, you cannot run a new model, right? So everybody should be free to do new things, and especially there are certain things we haven't settled. I think the structural uncertainty question is a hard one. I understand that there are issues of how many models can you usefully support. There is a resource issue as well. But I don't think the ideal number is very small. I think there is still a lot of science to be done, and there's a lot of ways to do it. Some things where there's less controversy, I think naturally people will migrate towards common things.
Thanks, Balaji. Chris, do you have any follow-ups?
No, that's fine.
Okay, great. So I think we'll move on to the next speaker, Balaji. Thanks a lot. The next speaker is Cecilia DeLuca. Cecilia, are you on the line?
I am.
Okay, great. I'm going to switch control over to your computer.
Yes. Can you see my screen?
No, not yet. Just hit the Share My Desktop button, and then we'll be able to see it. Okay, looks good. Whenever you're ready, go ahead.
Okay, great. Thank you. Right. So I'm Cecilia DeLuca from NOAA Israel and the University of Colorado, and Balaji, you gave a great entry point. So as Balaji mentioned, the 2012 NRC report called for common modeling infrastructure, but the calls for common modeling infrastructure went all the way back to 98 and before that, for people who recognized that there's a need to collaborate model development. So one of the very basic reasons for common modeling infrastructure is that climate model components come from different groups, and it's nice to have a standard to write to if you're trying to assemble them. There's also the motivation of wanting to lessen redundant code development. So some of what ESMF does is to provide utilities that are not really rocket science, but that we don't want every group to need to develop. So some of that cost effectiveness is part of the motivation for common infrastructure as well. There's motivation to improve the available infrastructure capabilities by pooling both resources and expertise. And I think that was part of the original vision for common infrastructure, too, where people thought that by working together, they might be able to address problems that one lab couldn't do on their own. And Balaji, I think, very, very capably addressed the issues related to controlled experimentation and the creation of flexible ensembles for research and prediction. So I would say, with respect to some of the more basic motives for common modeling infrastructure, that while some coupling problems are very complex, there are others, like changing to an alternate ocean, that are not especially complex, and that in some cases, and where common modeling infrastructure provides a relatively straightforward path to sharing components. Not in all cases, but I think there's a spectrum. So ESMF was developed as a multi-agency response to calls for common modeling infrastructure. And ESMF delivered standard interfaces for model components and high-performance libraries and tools for time management and data communications, and especially important, parallel grid remapping. So I'm going to talk a little bit more about standard interfaces and parallel grid remapping next. A couple of metrics over on the right. ESMF currently has about 5,500 downloads. We test on about 40 different platform and compiler combinations, and have an exhaustive suite of regression tests. So it's quite robust at this point. So what does the standard interface look like? All ESMF components have the same three standard methods: initialize, run, and finalize. Very basic stuff. And each standard method has the same simple interface. There's a component pointer first, and then there's a set of inputs, and then there's a set of outputs, and then there's a clock to control the time stepping and time and alarm information. That's what we mean when we talk about a standard interface. ESMF grid remapping is perhaps the most popular utility that ESMF has, both used within the framework and used as a separate package. So it's, I think, uniquely fast, reliable in general. the interpolation weights are computed in parallel in 3D space. Both logically rectangular and unstructured grids are supported, global and regional grids, 2 and 3D grids, many interpolation methods, even options for straight or great circle lines between points, masking, and a variety of fold treatments. There are multiple ways to call this. You can call it through the ESMF API within a model. We have a Python interface now, which has become very popular. Probably about a quarter of our downloads are for this Python interface at this point. And we also have an offline utility where you can generate interpolation weights from grid files. That's also become very popular. So using ESMF doesn't mean just one thing. So one way of using ESMF is just to wrap components. And to wrap components, you use a relatively small amount of the framework. So, for example, here you might just want to make your ocean model available to the broader community with an ESMF interface. Another way of using ESMF is to remap grids. And here you're using much more of the framework. There's a lot of investment in the infrastructure for this grid representation and remapping. So you might want to use that for a modeling application, either with ESMF components or with your own components. Or you might want to use it for a data analysis and visualization application. So ESMF is currently being used by this suite of packages at the bottom here, including NCL, PyFerret, a whole bunch of data analysis and visualization packages who were challenged, especially by the grids that were that the CMIP5 models were on, which they really didn't have the resources or the structure to deal with, but ESMF did. Finally, you might want to go whole hog and construct couplers and coupled systems with ESMF. In that case, you're really using all of the infrastructure. You're sequencing components, you're transforming and communicating data among components, and you're using all of the utility infrastructure, probably the time and I/O and utility operations and all that stuff. So this chart is just another quick way of looking at that. As you can see over on the right, you're pretty much using everything. If you're constructing a coupled system for remapping grids, you're using part of it, and for wrapping components, you're really not using much of it. So let's look now at what NOAA is doing. So the NOAA Environmental Modeling System, NEMS at EMC, is where ESMF is mainly tested and run at NOAA. And these ESMF interfaces provide a way for the NOAA and other research centers to interact with EMC. So here we see, yes, EMC is doing the whole hog, couplers and coupled system construction, and Esrael and GFDL and the Space Weather Prediction Center are wrapping components to give to EMC and other sites as well. We also see on here that NOAA PMEL is using ESMPy, the Python package, in PyFerret. So across the board, the NOAA sites are using ESMF in a variety of different ways, but ESMF is linking these sites together. Okay, a word about research. So ESMF needs to innovate in order to stay viable. Nobody wants to use a last generation framework. So ESMF works with research teams that provide cutting-edge requirements and that test and evaluate and provide feedback on ESMF capabilities within their applications. So it's really important here that the group that we're working with, the research group, actually runs much of the framework. So they need to be really to provide feedback in the category of using the grid remapping at least, or using the fully coupled system. And so GFDL and Esrael have helped to inform ESMF design in many ways over the years. But our active research partners, the ones that run the software and provide feedback on some of these grid and other more intrinsic capabilities, are largely outside of NOAA. They include CESM and DOE modelers, Navy modelers, NASA modelers, and many users of the ESMF grid remapping tools, including the UK Met Office. And often these interactions are funded through research calls, but they really make it possible to create ESMF infrastructure that's sufficiently flexible to be appealing. So looking at other centers, who's actually using it to create coupled systems, CESM, the Navy, and NASA, in addition to NOAA, and a variety of groups are using it for grid remapping. And just about every, of course, everyone who's using it for the coupled system construction also needs to wrap components. So what happens is that we get a tremendous number of requirements in from these groups that are using challenging grids, for example, like the home grid at NCAR, which is almost fully unstructured, or the MPAS grid, or the ORCA grid. And that really pushes, and all of these data and visualization groups that need to pretty much handle anything that anybody throws at them. ESMF gets those requirements and really needs to step up to those challenges, and that helps to make the software viable. So a couple words about performance. We regularly do performance reports. We test against other packages if we can. We usually use DESM because it's easy. And we post reports on this page. If we compare against another package, we review those reports first with the folks who develop the other package. The sorts of performance findings we have on that page, the ESMF component overhead is typically negligible and going out to about 16K. It's about the same as the DOE implementation of infrastructure in CESM. So on this page, at this link, there are user feedbacks from folks from NCAR CGD, NCAR M3, COLA, the Navy, NASA, and other organizations that are commenting on their use of the ESMF software. And sort of the sample statements, the task would have been impossible without the regridding capability. It made it possible to access a large class of data that we couldn't before. It's allowing us to provide users with more functionality than we could before, and so on. So the themes that you'll see if you go to that page are that ESMF grid remapping allows users to work with grids that they really just couldn't work with before, that the tools are fast and reliable, and that the customer support is excellent, which I think it is. So a word about governance and partnerships. Most development tasks come from user emails to ESMF support, and tasks that are longer than 2 weeks are prioritized by a change review board. So we get a bunch of representatives from our main user groups together and go through a formal prioritization process. Other pieces of the governance are an executive board of people who tend to be at the sort of director level, and we also have an interagency working group of project sponsors. So this is the funding breakdown. It's very diverse set of funding sources from NOAA, from Navy, from NSF, and from NASA. The new directions. The ESMF initial software fell short of the vision for common infrastructure, I think, in several ways. So you saw the very general component interface that we have. You can use that in so many different ways. I mean, we really had very few constraints with the initial ESMF distribution about how you would call that interface, or what kind of coupling interactions you would have. So the implementations of ESMF could vary widely and didn't really guarantee a minimum level of technical interoperability. So another issue is that it was difficult to track who was using ESMF and how they were using it, and there was a significant learning curve for implementing ESMF in modeling code. And new development directions address these gaps. So the first of those is being addressed by the National Unified Operational Prediction Capability, or NOAA. That's a consortium of operational weather prediction centers and their research partners. So they developed this thing called, in collaboration with us and with the broader community, called the NOAA layer, which adds to ESMF a formalism that describes and splits the phases of initialization, so that if you're bringing two models together, their initialization portions will kind of merge and fit together. There's a formalism for checking and reporting whether component requirements are satisfied during the run sequence. And there are code templates for drivers and models and mediators and connectors. This is all still very flexible, but there's enough structure so that you could at least describe what you're doing. And therefore, you can check what you're doing and make sure that the codes technically will fit together. And these code templates do support a variety of model interactions, for example, explicit or semi-explicit or implicit coupling, all of which are supported. And it also provided compliance checkers so you can tell when you're developing a component if it's going to fit within the system or not. So another issue was that it was difficult to track who was using ESMF and how they were using it, and this ESPS idea is intended to address that. It's a collection of weather and climate modeling codes that are using ESMF within WASP conventions. And there's some draft inclusion criteria on that page. So currently, components in ESPS can be coupled system, atmosphere, ocean, wave, or CI. So it's really the big stuff. And target codes include CESM, NEMS, which Mark will be talking about, including CFS v3, the MAPP and HICOM oceans, the Navy global and regional models, and the NASA GS5 and Model E codes. And this is just it's an eye chart showing those codes along the top axis and along the left axis what the components are within those codes. And so, although there's a lot of complexity, as Balaji was describing, there's also, as he was describing, a lot of reuse of components in these codes. So you can see HICOM is used across a bunch of the codes, and MOM5 is used across a bunch of the codes. And what we're finding as we're developing this suite is that we can take a version of HICOM that was developed, for example, by the Navy, and use that as the basis for starting a HICOM coupling at NEMS, and use it as a basis for a HICOM coupling that's starting within CESM. So we are seeing the same code with the same bindings being able to be used at multiple sites, and I think that's part of the objective for creating some of this common infrastructure. A little bit of vision versus reality. Some documents had called for a single infrastructure that would replace all the existing infrastructure, and that's not really what we're doing. What we're doing is wrapping, for the most part, native infrastructures so that GFDL and CESM can keep their native infrastructure while still being able to run with the ESMF and WAPC conventions. The last item was this Cupid development and training environment, which addresses the learning curve for implementing ESMF in a modeling code. And the goal here was to make ESMF training and development a little simpler and more appealing. So with this integrated development environment, you see a multi-screen user interface where you can pick a training problem or a coupled model. You can see a trace of the model structure. You can navigate around the model. You can modify the source code. And really, it's really pretty cool that you can automatically generate some of the code needed for MOPC compliance and then run and test the code, make sure it's compliant, and then run locally or on a cloud. So we're working on a prototype that's expected to be, so we have a working prototype. We're expecting a first release this year. A couple of screenshots where you select the code, you get the multi-screen editor, and you can run locally or on a cloud. So coming in 2014, we have a BAMS paper in progress describing ESPS, and we're anticipating completion of at least initial versions of coupled NEMS with MOM5 and HICOM and CESM and HICOM before submission of that paper. For ESMF development, we're doing some work with Navy and DOE on accelerators under the ESPC program. We're replacing the finite element mesh library. This is a very flexible infrastructure inside of ESMF with a package from DOE because we'd like to leverage their development. We are adapting remapping so that you can use it with observational data streams, and we're planning to introduce a higher order conservative method. So, it's not all that we'll be doing this year, but that's just a sampling. And we're also planning the first public release of Cupid, kind of embedded in a better outreach plan. And we'll have a new research and outreach lead coming on this year. So last slide, why is ESMF different? What makes ESMF different from the center-specific framework? So to satisfy many incoming research and operational requirements, ESMF developers, we had to design for a very wide range of grid, data, time, and component structures. And that creates a great flexibility that supports knowledge transfer. So if you have had to, design for an incredibly high-resolution grid from NASA, it's likely, if you're using the same infrastructure at NASA and a bunch of other sites, that the infrastructure will be ready at the other sites if you want to migrate that component over to the other site. So it's kind of a way of getting the infrastructure everywhere ready for anything. ESMF infrastructure is built for deployment, and it's well supported. it's resource effective in that its development is shared among agencies, and its development priorities are set through a clear, formal multi-agency process. But I think most important, ESMF really spans the often artificial bounds of modeling efforts within agencies and efforts across agencies and across weather and time at climate scale. That's what I've got.
Okay, thanks, Cecilia. For virtual attendees, please send me a question for Cecilia using the chat feature. Any questions here in the room, or from Balaji or Mark on the line? Okay, I don't see any questions here, so I'll wait a few seconds.
Well, in which case, Cecilia, thank you. That was very good. This is Rick Rosen. You happily did, at least happily from Balaji's perspective, didn't use the words plug and play anywhere. But I had the sense that the coupler component of ESMF was built with some of that in mind, although Balaji's presentation indicates that coupling is a bit more complicated than just a simple black box.
So Rick, let me stop you there. Coupling in ESMF is not a simple black box. There's no single coupler in ESMF. So you customize your coupler within ESMF, and ESMF supports many, many different kinds of coupling.
Good, thank you. I thought your answer might be going in that direction. I'm finding this very interesting, very enlightening. Thank you.
So there is one question. Oh, sorry, Cecilia.
Sorry, go ahead.
There is one more question before we move on to the next speaker from Krista Peters-Ladard. So, Krista, are you on the line?
Hi, I'm here. Can you hear me?
Yeah, absolutely. Go ahead.
Great. Yeah, hi, Cecilia. I was just wondering about land models. I noticed that wasn't in the chart in terms of defining compliance for the Earth Science Prediction Suite. So how are you going to support land models and define compliance with respect to the coupling with the atmosphere or ocean models?
That's a good question, because we have groups that have ESMF compliant land models. And we have groups that call their land model as a subroutine within their atmosphere. And quite frankly, I think we're waiting for the community to kind of converge around strategy. At this point, to me, that question is going to be deferred for a little while. Mark may also have some comments about that, because he's working with another physics interoperability group within NOAA that is also looking at land models. So I think land is still an open question about whether we want to try to have a structured interface around that.
My point in that physics interoperability, we're looking to bring in some land expertise within that group. So we haven't really started looking at it yet.
Yep.
Okay.
Okay, thanks.
Thanks for the question, Krista, and thanks for the question, Rick, and thanks for the talk, Cecilia. So we're going to move on to Mark next. Mark, you're on the line, right?
Okay, can you hear me?
Yeah, if you could speak up a little bit more, that would be helpful, and I'm passing control over to your computer right now. So just hit the Share My Desktop button, and we'll be able to see your screen.
Not clickable. Oh, okay. Can you see my screen?
No, not yet. Did you hit the Share My Desktop button?
I thought I did. It said you. All right, let me try again. Oh, yeah.
We need it in WebEx, yeah. Okay. Yeah, go full screen.
Yeah. Okay, you can see it.
Great. Yeah, go ahead whenever you're ready.
All right. So I'm Mark Iredell, but I'm really speaking for the whole NEMS group at NCEP and EMC And actually, it's not just NCEP, it's other localities in NOAA, too, that are participating in NEMS development. I'll make my talk brief. What is NEMS? It's the NOAA Environmental Modeling System, which we started developing, I think maybe about 8 years ago, as a piece of software that can contain and also have tools for high-performance models. Its intended use was for the operational prediction models at NCEP. And so the initial intent is not to be a community model at all. I just want to make sure everyone's clear about that. It's to run our forecast models within the Weather Service. And but we were hoping for eventual support to the community through the Development Test Center, and we're still working on that. Okay, so what's our motivation? I sort of went through it a little bit, and we want to have a superstructure that can be shared by NCEP models, and it's similar motivation to what Balaji and Cecilia mentioned, that we have all this expertise across different institutions that we want to bring in to at least have some shared things that we all do. We wanted to modularize and have a standard interface for the pieces of the models, and we use the ESMF components and interfaces for that. We also wanted to work on having some standard I/O within our models, and so we have an isolated history and restart write component that's common, that's intended to be common for all the models in our system, so that models do not have to figure out how to do the most efficient I/O. They just pass their data to this write component. Initially, we didn't want to do any intrusion into the science code and the parallelization that's already been done in these models. Now, that's not a final word. We will probably bring in some more infrastructure into these models as the different requirements of new computers become even more complicated, and we don't want to have to solve the same problem in each of our models. But we didn't want to abandon what had already been tested at being efficient in our current models. And so that's what's the current state. And so this is the NEMS structure. And it starts off at the top. It's a single application that runs in a computer. And so it does have a single main, and then it calls the NEMS component, which is an ESMF component. And basically what NEMS does is it instantiates many Earth components, as many Earth components as requested by the user. So this is, we instantiate ensembles right at the top. And we can also have this Earth ensemble, and the number of Earth components here is labeled NM, but in many cases it's just one if we're not running an ensemble mode. And then this Earth ensemble mediator is our coupler of the different ensembles members, if you want to couple them together in some way, statistically or something. And then if you, let me use my mouse. Then you can walk down to what the Earth component does is it calls an ocean and an atmosphere and an ice, and has a mediator between atmosphere and ocean, and we'll eventually have a mediator to the ice. And so basically the Earth instantiates its individual mediums. And then if we dive, I don't have any details about ocean and ice, but dive into the atmosphere. The atmosphere has right now 3 different choices for full models. The nested model that we run in mesoscale mode in operations, the global spectral model that's in that runs our global model and operations, and the FIM from ESRL, which is the finite volume icosahedral model. And then these guys are, again, broken down into components, well, some of in different ways now, up to the model developer to figure out what they want to do. And I'll look at the GSM, for instance, has a separate dynamics and physics component, plus a chemistry component, and then it calls the shared right component to do its I/O. And then there's couplers in between all these things. And to talk to Rick Rosen's point, these couplers are rather they have a lot of generic code in it, but they're also pretty specific to what they are coupling, because they understand what kind of fields go between physics and chemistry, et cetera. Okay. So the NEMS is now in operations, has been since 2011, when the NMB, which is our mesoscale model, runs 4 times a day with static nests, which means there's a parent, and then there's a nest underneath it, and four nests underneath the parent. The parent is the North America. The children, one is the continental United States, another one is Alaska, another one's Hawaii. And then there's even a grandchild nest underneath the continental U.S. for the area of interest of the day that we can run at 1.3 kilometers. And then in 2012, we implemented the NGAC, which is the GFS aerosol component, which, if I go back, utilizes this chem to do its aerosol chemistry, and then moves the aerosols around by the rest of the model. And that's been in operations for over 2 years now. All right. Cecilia mentioned the NOAA layer, and we are invoking it now into the NEMS. And I'll skip down to here. Let's see. It's as Cecilia mentioned, it makes the use of ESMF more tightly constricted with what metadata you use, and everything has conventions and templates. Right now, we're using ESMF 6.3.0R with the NOAA code that's in that version. We're using it in the atmosphere-ocean coupling in NEMS, and as Balaji mentioned, just today, we finally got the two-way coupling of the GSM and MAPP working. Both the fluxes are moving back and forth. They're running in concurrent mode. And now comes the scientific effort of tuning the coupling, or perhaps it's debugging. As Balaji mentioned, the SST was going a little bit out of control just in our 7-day forecast. So the first test is rarely, I'm glad it got to the end of the forecast, actually, but it has anomalous evaporation and everything as the SST is running away. So we've got now, we have the hard scientific work of doing the coupling. All the software is working now, but when I say tuning here, it's mostly, some of it's debugging, but mostly it's figuring out how the fluxes need to be exchanged and everything like that, which is more of a geophysics type work. And this is how the coupling looks like. We have the main, and then as I showed in the earlier diagram, the main calls the NEMS component, which calls the Earth component, and then underneath the Earth component are an atmosphere and the ocean. The atmosphere, for instance, is a GSM, and the ocean could be, it's instantiated differently, but it's more or less the same idea. It could be a MAPP or other oceans. And the mediator is user code that does the coupling. So it has a lot, the mediator could have a lot of science in there dealing with, what kind of fluxes, how to interpret the fluxes and pass them on, or how to interpolate them. And then these green arrows are involved, the data movement between atmosphere to mediator, ocean to mediator, mediator to atmosphere, and mediator to ocean. And these are more generic type ESMF calls. But the mediator is what we would call user code. The scientist actually gets in here and works with it. And as was brought up earlier, we have a physics interoperability group, and we were trying to create this standard physics call within the atmosphere, so that we have a standard for 1D physics, sort of a standard interface for any dynamics. And right now we're trying to work on it so that we call it the GFS physics, but from, let me go backwards a bit, but from any of these models, we want to be able to call the GFS physics from this model, with this model, with the same interface, so that all your static fields that the physics needs and everything, or get to the right grid and everything. And it's turned out to be rather a challenge. We can write down what we'd like to see it do, take care of its own diagnostics, take care of its own initialization, et cetera, but getting any model to be able to call it this way it turns out to be a lot of detailed work. And so what's our delivery plans for NEMS? Early next year, well, it could be, it says 2015. That's really fiscal year 2015, so that's actually fall of 2014. The GFS should be in the NEMS, and same with the global ensemble. The global ensemble might be a couple months after that. And when the GFS is in NEMS, the post-processor will be in NEMS, because we run a post-processor inside the NEMS. I didn't show that in the diagram, but that's part of the right component, is the post-processor, which used to be an external application. And hopefully we'll include a NOAA CPO physics driver. And in 2016, I'll go through these really quickly. We'll have the whole atmosphere model, which goes up to 600 kilometers high in the atmosphere for space weather purposes, coupled ocean atmosphere, hurricane modeling with two-way telescoping, hopefully a tiled land model by that point. Well, it's not really, and net CDF output, NMB, which is their mesoscale model, nested inside the GFS and running at the same time, multi-model ensembles running at the same time, and the climate forecast system. So in summary, we are building this NEMS, and maybe we'll never finish building it. It's a continuous upgrade process to unify the operational systems under a single framework, and so we can share common structures that we don't need to reinvent each time, and that would help expedite interoperability. Expedite's a good word for it. It doesn't mean plug and play, but it just helps in some way. And the first two systems have been implemented already, with more to follow. We'll make collaboration with other groups less difficult, hopefully, and we're going to include this NOAA CPO physics driver. Thanks.
Okay, thanks a lot, Mark. Any questions here in the room for Mark while I wait for people to type them in online? Or questions from Cecilia or Balaji? All right, so I haven't got any questions online. There are none in the room, and we've actually been booted out of the room. So we will conclude, and I'd like to thank our three speakers, Mark, Cecilia, and Balaji. Thanks so much for this overview of model infrastructure efforts. It was a really nice, diverse set of talks and very interesting overview. And thanks to everybody for attending. So we have another webinar coming up next week, April 8th, Tuesday, April 8th. It's on the topic of climate extremes, and we have 4 speakers, Gabe Becky from NOAA GFDL, Chris Thorncroft from the University of Albany, SUNY Albany, Scott Weaver from Climate Prediction Center, and Kinsey Mo, also from the Climate Prediction Center. And this webinar is co-hosted with the Earth System Science Program. So I hope everyone will join. It starts at 1 o'clock and next Tuesday. And again, thanks for attending. Thanks for the talks, and we'll talk to you hopefully next week.
Excellent.
Thank you.